You may notice I'm not Gary. I'm Paul again. And Gary, unfortunately, cannot be here, so I'm going to present Gary's work on the Heterogeneous Accelerator Toolkit, or HAT, as we like to call it. So I'm going to do my best job to channel my inner Gary here and present his work. So I'm obviously going to talk about HAT, about what it is, and I'm going to, at a high level, talk about the programming model, which is related to Brian's question. I hopefully will help answer some aspects of Brian's question about this, and explain how the Babylon and Panama actually help this. I always envisioned when we started Babylon that Panama plus Babylon would be greater than the sum of the parts, and I think this project tends to prove that out. So HAT is really four things. It's a kernel-like programming model for writing kernels. We call this an ND range style parallel programming model. You could think, if you're familiar with CUDA, it would be a grid-like parallel programming model. And the reason why we're leaning into this is this idiom is very familiar with existing GPU developers. So any GPU developers who are in OpenCL or CUDA would be very familiar with this model, or even Tornado VM as well. But it's also familiar enough, if you understand it, for Java developers as well. You have to shift your thinking a little bit, but maybe some Java developers already done that. We'll get onto that and why it should be familiar. It's not the only style of programming you can do for kernels. Steve showed Triton before. There's OpenMP, there's OpenACC or Tornado VM loop-style annotations. HAT it should be possible for others to plug into HAT these kinds of models, but we're not going to focus on them in HAT. And so HAT provides this layer on top of the JDK, and underneath the cover, it can leverage the CPU or the vendor's native runtime for GPUs. In addition to a kernel programming model, we have a compute programming model that describes how you dispatch or call kernels. Kernels can be called many times. The data can come in and out, and we want a model that describes or talks about that kind of interaction. And then we have a data model. We need to describe how data communicates between the host or the compute and the kernels. And because GPUs have a different address space to CPUs and a different kind of memory layout or way they interact with memory, we need to deal with this very carefully. So we need to describe how we do this, and we are going to model these kinds of rich structures using Java interfaces. We're not going to use standard on-heap information or allocations on the heap. We're going to go all off-heap. And there's a pluggable backend. So the last is not the least in some sense. This backend will allow vendors, Intel, NVIDIA, AMD, or FPGAs to plug into this system with HAT helping them do some of the work to generate the code specific for the GPU or the FPGA or any other accelerator that may come along in the future. That's general. So what is GPGPU compute? It's kind of funny that we still call them graphical processing units for our purposes. They're general parallel processing units. I believe, I'm not an expert on the history here, but I believe when GPUs were used, some clever enterprising people managed to do linear algebra using the sort of graphical APIs that would usually render polygons or do vertex translation. And they managed to get the inputs and outputs for matrix multipliers in there. Quite clever. And over time, people realized they could do more parallel kinds of work on these computing hardware. And I think what really changed it was in the sort of early 2000s or mid 2000s, there was a shift in the hardware design of GPUs, I believe. Please correct me if I'm wrong, where they devised a single instruction multi-thread hardware. And in combination with that, there was devised a software platform. So the two, software plus hardware together, are extremely important here. And what we look now is that the one that got this right has an astonishing market cap right now. Probably gone down a bit today, given the stuff, right? But astonishing market cap. in this area. And this last link, I think, is very useful for me to understand the difference between single instruction, multiple data with vector hardware and simultaneous multi-threading you get on CPUs. The GPUs fit in the middle here, and they compromise because CPUs are really good. A single hardware thread is really good at running sequential code very, very fast. The GPU is really good at running concurrent code really, really, really fast. But sequentially, it doesn't run it fast. It context switches very efficiently between lots of tasks. And so that's the single instruction multi-threaded model. But if you have control flow in there, it tends to slow down because different threads have to wait until you get join points in. So there's a compromise here, but it works extraordinarily well. So in Java, there's many pain points to using Java prior to Panama, and still pain points today with Panama. Initially, people would code using JNI. I don't want to code using JNI anymore. I want to code using Panama and JExtract and all that. And we see Steve talking about that, binding to the Intel 1 APIs. We can bind to CUDA APIs. This makes our life so much better and so much more productive. Later on, there were libraries and platforms like Rootbeer, Aparapi, and Tornado VM that allowed you to extract or translate bytecode to kernels and do the heroics there. That's harder than it should be as well. And code reflection will help make that easier. So the main point here is you can do it, but it's hard, it's messy, and it's potentially, as a Java platform evolves, you may be using internal stuff that may break you as well. So we're going to make this a lot better and a lot easier to do and a lot more stable to do. At the time when these libraries are being developed and developed now, they have certain limitations in the inputs and outputs to kernels as well, and have certain limitations in the efficiency they manage data between the GPU and the CPU in terms of copying. Copying is a costly operation between the host and the GPU. You have to minimize these things. And so the more copies you have, the more that the GPU can't do its thing, doing all the parallel processing. So this is all great for single kernels, but most real-world applications there are arguably multiple kernel. The host may interact and call multiple kernels to do its job. And this is where some of the current state-of-the-art falls down in regards to that. So back to the first part of HAT, which was the kernel programming model. We're calling it an ND range programming model. So let's describe a little bit about what that is. So take, for example, the code on my right-hand side here. We have a simple for loop, and all it's going to do is square the numbers in an array and put them assign them back to the array. Nothing too complicated. This example is going to go through because it fits on slides. And it's easy to understand. So the range part comes from the loop, the for loop, going from 0 to up to, but not including the array length. That's our range here. And the little bit, the loop body, is actually the kernel. So we can extract out the loop body and turn it into a method where the method parameters, first method parameter is the loop variable, and all the other parameters, in this case just one parameter, is all of the variables that the loop body uses but doesn't declare inside it. And then we can effectively replace our arithmetic expression and update with the call to the method instead. And so we're calling our kernel. And now the bigger step, if you've ever used streams, you've already done this, you can move that method and call it from a stream instead. Sequential or parallel, and stream hides the implementation of how it loops. It will still range over, but it hides it. So it can go sequential, it can go parallel, and that's the trick of the GPUs as well. The GPU hides how you loop over this. It provides you, I'm going to range over this. I'm not telling you how I'm going to range over, or the order of execution in these things can go concurrent and in parallel, but that's the trick. And that was Sumatra's model, actually. They were translating parallel stream expressions and translating that square kernel into GPU code, particularly challenging for Sumatra because they were trying to, I believe, also emulate Java program details, behavior on the GPU, like supporting garbage collection and so forth like that. It was particularly challenging. And also potentially limited to detecting stream expressions as well. But that's the idea of the kernel. It's actually very simple, and many people are probably doing it without realizing it with streams. So hat leverages current and proposed Java features. So we're going to use Panama, way better than JNI. And we're going to leverage the heck out of memory layouts and memory segments. So memory layouts will enable us to describe the structure of memory, and memory segments will enable us to allocate efficiently off-heap memory that we can communicate between the host and the GPU. So the idea is we can leverage this better to minimize the copies between the host and the CPU. And Babylon will give us the ability to translate symbolic descriptions of Java code into executable GPU code, a bit like what Steve talked about when I showed you in those translation graphs, if you like. This will allow you to do it much easier than lifting up bytecode or trying to work out, operate on the AST of the Java source compiler. So let's revisit our squares example in the context of a hat programming model here. So here we're just going to copy our square method like before, put it in a square class. And the first trick we're going to do is we're going to replace the int array with an interface called S32 array, which is an array of signed 32 integers. So we may be able to support primitive arrays later, but we're focusing on this interface abstraction for now in the way we're modeling data. So we replace the on-heap data with an interface that will actually encapsulate off-heap data. And we'll talk about that later. So we got a square here, a square method. We replace the int array with S32 array, and the same code before, except we're operating on the S32 array, and we don't have the nice array-like semantics as before. And then we have another method called Kernel, which takes a kernel context. Steve showed that before there. And a kernel context is the way we get the index we're operating on and pass it to the square array. So this is how we range over it. You can think of KCX as the identity of the kernel we're operating on, the current identity. And so that gives you the potential parallelism. This kernel method is going to be called many, many times concurrently. And so we delegate to, a kernel method delegates to square. So we notice we annotate these with code reflection. We need to reflect over these because we're going to translate this to PTX or SPIR-V or OpenCL C99 and so forth like that. So we need to reflect on both of them. So this kernel context is the thing that gives you a little bit of abstraction between the different GPU implementations out there, like OpenCL and CUDA. They have different ways of getting the current piece of unit of work that you're operating on, i.e. the index into the array that you want to operate on. So we try and hide that there. We know we're only supporting, actually, it should be called a 1D array programming model right now because we only support 1D range. It's not clear we need to support 2D or 3D. Feedback would be useful in there because you can compose 2D and 3D from, you can implement 2D, 3D in 1D, but I think most GPGPU kind of problems don't need the other cases perhaps as much, but we can support it if we want to. That kernel context is also the way we can support concurrency between threads and GPUs as well. And so we may have methods on there that can synchronize threads. And then the vendors would implement that according to the appropriateness on the platforms. It may be a way we also do allocation on the GPU as well. And it may be where we offer high-level functionality, like prefix scans, sums, maybe vectors. We're not sure yet. We need vendors to help us work out what the common denominator is here and whether you could cast a kernel context to a sort of level 1 context to get to level 1 functionality if you're using Intel's APIs. So we can, of course, collapse this. You don't have to separate this out. The point being is you're not restricted to collapsing. You don't have to compromise here if you don't want to. Plus also separating out may be useful for testing. So once we've got our kernel, we need to call it. We're calling, in hat context, we need to dispatch to the kernel. And so we need to write a compute method. And so here we have a compute method highlighted in green. And it takes a compute context. And the compute context has a method dispatch kernel. And we call the kernel through a lambda, passing in the arguments we want, like so. And to execute that compute method, we need an accelerator. So we create an accelerator. The accelerator can choose the kind of hardware it wants. And once we have an accelerator, we can compute, calling a compute method, and call the square compute method for a lambda expression as well, like so. So that's how we connect it up. And in fact, what's going on here, as I showed in my first presentation, what we're really passing is quotable lambda expressions to the compute and to the dispatch kernel. And we can just collapse it all into nested lambda expressions we want to. And that's that double, I can't remember what I called it, one of the last slides I had in my prior presentation with the sort of layered programming models going on here. There's two programming models here. One is in yellow, which is the kernel programming model, and one is in green, which is the compute programming model. And they have different restrictions on what you can do and what. Of course, you can even go further and say, for simple cases, I may just, from the accelerator, just dispatch the kernel. We haven't decided yet. So the accelerator plus the backend you choose here has complete control. Once a quoted lambda is passed, it can see into everything, into the code of everything in here, and analyze it. So if you're going to run this on a GPU, you might be disappointed, because if you set a breakpoint, you wouldn't break on the GPU at all. It would just run on the GPU. And your breakpoints wouldn't work. However, if you run this on a Java backend, you set the breakpoint would work. And so we can implement, this code can run on Java, multi-threaded or sequential, single-threaded for debugging, or compile it to SPIR-V or PTX and run it on the GPU. So even if you can't debug on the GPU step through, you can still run it on Java first and debug and test it out before you decide to switch to the optimal route. So this gets to the point of Brian's question to Steve as well, is that there are restrictions on what you can do in kernels. We're still working out what those restrictions might be, but it's kind of like coding in C-like way in some respects. You can't allocate on the heap because there's no heap on the GPU. We're not emulating the Java runtime on the GPU here. There's no exceptions, no object identity. We can't do reflection, no code reflection on the GPU either. So no access to traditional objects. So we're trying to limit it down here. So we don't, and HAT is just a library on top of the JDK. It can't go into the internals. It doesn't know anything about how Hotspot lays out memory for objects and so forth like that. But kernels can access their args. They can perform basic arithmetic operations. We'll show some fairly reasonably complex examples. They can call other static methods, math methods, and so forth. If we choose to support like the math, like mathexp or log, we can make those intrinsic and translate those to the equivalent calls on the GPUs. And they can contain control flow. So we can use for statements, while statements, even switch. And I think if we can pattern match with the constraints, the other constraints, we can even support that. Of course, when writing GPU code, if you're going to use control flow, that's going to impact your performance. So the compute model has far less restrictions. What we mostly need the compute model for is to analyze how kernels are called and what data is input to them and what results they return. What's effectively, do I write to this thing? Do I read to this thing? Do I do reads and writes to this thing? And so forth like that. But we also may need visibility into working out, oh, this kernel has no dependencies on this kernel. I can run these two concurrently or let the GPU work it out. And then at some point, I can join later. So you could actually, potentially, the compute may have an asynchronous nature to it that's hidden to the user. But we may be able to go async under the covers. So under the bonnet here, when we call ACC compute, we construct a compute context. And the compute context contains all the code reflected methods that we have. We call this a compute call graph. So the compute method, lambda is reflectable. We know we're calling square compute. Compute is reflectable as well, so we can analyze that. And so as I showed in the prior slides, is this module of code we can have access to. And then we can do the same for the kernels as well. And so we can pass all this information over to the back end, and it can do its thing. So I've already said some of this. Presumably, once you've got a kernel, but you've got to do something with it. So if you've got an OpenCL backend, you're going to generate either SPIVy or OpenCL C99. And it's going to want to know about what this backend does. It's going to know, does it mutate data and so forth like that? Does any of the code and the compute access and mutate data as well? So we know does the host mutate? Does the kernel mutate? If we know these things, we can optimize data movement. And the thing that really distinguishes the existing libraries and platforms in Java is we have visibility into the compute call graph. What kernel is called when and what the dependencies are. And that we can write that in normal Java. We don't have to compromise and write it in a DSL where we can't express loops and conditionals, which is currently what you have to do with Tornado VM. So we can write natural code that dispatches kernels. So that's a bit on the code reflection side. When I get to demos, you'll see some code models fly by. I'll show you what's going on, get a bit more concrete on that, and you may see some OpenCL C99 code fly by. The second part is around mapping memory segments to interfaces, the data model side of stuff. This is still early days that we're working on, so I think we're going to cycle around a few iterations of the design of this, but I think we're onto something. So the problem is we've got the host and we've got the GPU. They have separate memory systems. So you can't pass a reference to a Java object over to the GPU and expect it to work. You're going to have to copy something over. And you don't want to copy over the contents of the object. That's private to a hotspot and private to its runtime. When we're building a library, we do not want to depend on the implementation details of how hotspot lays out its objects. So Panama is the key here. This is what's going to really help us, because we can use memory segments to describe the layout of off-heap memory, and we can, memory layouts to describe the off-heap memory, and we can use memory segments to allocate it off-heap, and we can use memory segments to allocate memory where it's contiguous, and we can effectively describe what it does. So last year, Gary presented, he had a prototype proxy that did this kind of thing, where you could have an interface, a layout, and a memory segment, and it would proxy to the memory in the memory segment from the methods on the interface. But it's got much more robust now, thanks to Maurizio and Per Acker-Minberg. They had an implementation that did this much more efficiently for access to off-heap memory when on the host on the CPU. And Gary took this and has enhanced it and hatified it, if you like, to make this better. So say on my right-hand side here, we have an interface XY. It extends from a hat buffer that indicates this is something special to hat. And we just have accessor methods to access points X and Y on there, nothing too fancy. And we can describe that with a schema that describes the structure of it and the order of the members in the structure. Underneath the covers, it will generate a memory layout because it knows that int is the size of 32 bits. So you're going to generate a memory layout of that. We can ask it to allocate by giving it an accelerator. So when we allocate this and pass an accelerator, the accelerator can say, oh, I'm going to allocate this on the GPU and return a handle instead. Don't have to allocate it on the heap, on the host if I don't need to. And then we can access it. If we access it from the host, we may have to pull the data over and then update it in memory in a memory segment associated on the heap. We can get more complicated, that pattern there, we can nest it all inside the interface, API design sort of point here. The key thing is once we have this description, this schema, when we're translating to the kernel, and the kernel uses an XY type as an argument, we will need to do something with that type. And we translate that type to C schema like that on my right-hand side. So given this description in Java, we can translate the structured code for the struct containing X and Y there, And then when the kernel code is generated, and we see invocations of X and Y, we translate those to C expressions that access the members of X and Y struct, XY struct, like that. So if you want to generate C99 source, that's what you would use a schema to generate structs. If you're going to generate SPIR-V or PTX, what the schema will give you is a way to generate pointer arithmetic instead. So we can use the schema to do the additions to the pointers to get to right members of the struct. So the S32 array we showed earlier is exactly the same kind of thing. There's a schema that describes what it is. There's a way to allocate it. And in this case, Gary found a very neat trick that we can generate a structure like this with a zero-length array at the end of it. But if you allocate larger, you just overlay effectively the length and the array are fused together, like so, like that. So that's how we model it when we're generating C source. You can get more complicated. You can nest these things. So we can have say like an interface X, Y, W, and then we can have an array of these things, and we can generate the structure for this stuff as well. So again, there's an API design turn of a crank to get this right, I think. But I think we're onto something here in the way we describe this stuff. So here's a more complicated example. And so this is the game of life. And I presume everyone is mostly familiar with the game of life. It's effectively a convolution. You go over all of the pixels, and you decide whether a pixel is alive or dead by looking at the values of the pixels around it. And the naive implementation takes a big array, 2D array, scans over it one by one, doing the calculation. And so we can write that calculation as a kernel in the HAT programming model. And you can see this is fairly basic Java code, fairly readable, control flow, method calls. It's restricted to using control and cell grid here, which are HAT buffer interfaces. And so what we have here is a kernel that says, given a pixel, are you alive or dead? And update it. So we got, you can see the logic in the control flow logic here, and it's calling neighbor, and neighbor does some calculation on the cell grid. We'll explain that in the next slide. So it's fairly reasonable. This is not the most optimal way to write game of life, but it's probably the easiest way to write it. So the trick here is we want to avoid memory copies between the host and GPU. The grid could be a very large piece of memory. We do not want to copy this from the host to the GPU and back again for every iteration. Instead, we want to use a trick like double buffering. So what we'll do is we'll allocate twice the size of the grid, and we'll have two int pointers that flip between the two. And when one is we'll calculate in one buffer and display in the other, and then flip. So we're only flipping ints instead of flipping the whole grid. And that's what we're doing here. So we have a cell grid, which is effectively a large array allocated with twice the width times the height. And we have a control with int pointers that point into the buffer. So this is how Gary wrote this to reduce the copying between the host and the GPU for the grid when you don't need to display it. So then our compute model is shown like this. We have a loop in a compute. We say, well, we're going to view this, so we need to ask, while the viewer is visible. If it is, we dispatch to our kernel. The range we dispatch over is the grid width and height. And our kernel we're calling life before, passing control and grid in. So the arguments to the kernel are the actual parameters the lambda expression captures, control and grid here. And KC is an argument coming into the kernel. And then we swap, once we dispatch to the kernel, and the kernel completes, we just swap the pointers from and to. And then if the viewer is ready, we'll update the grid. If it's not ready, we'll continue and do another iteration. So if a viewer isn't ready, we shouldn't have to copy the grid over from the GPU to the host. It should just be left on the GPU. But in a naive implementation, every loop through this while loop will do a copy of the grid every time. So one approach we can do to the compute is to transform it. Because we can reflect over it, we can take the compute code and we can transform it, and we can inject tracing calls into this to track what's going on with the instances of control and instances of grid. So this is, I'm not going to go into detail in here, but this is, Steve had a transformer that did a transformation of the phi nodes for SPIRV. This is a transformation that injects tracing calls to tell whether we're pre-mutating, we're post-mutating, something escapes or not. So we can actually do a better job at optimizing memory movements. So the equivalent on the left is transformed into an equivalent of the right in the code model. So we take the code model of the one on the left and we transform it into a code model that is equivalent in source to this. So we add pre and post accesses, pre-mutates, post-mutates, and we also add pre-escapes and post-escapes because we're calling viewer update on grid. We don't know what viewer update does. We can't reflect into viewer update. It's not visible to us. But we know grid is important to us, and we know grid escapes. What does update do with grid? It could read or write to it, it could do anything to it. And so we've got to be conservative there unless we have a way of marking that viewer update, I promise I only read. So once we have this, we can be smarter in our copies. So if we go through and we don't call isViewer for update, is ready for update, then we don't need to copy anything. We just carry on going through. Only when we need to view it do we copy it. But this principle can be applied to other things, I think, too. The important thing is we can translate the compute and put tracing in if we want to. We can translate the kernel, not only to PTX, but if we translate it to PTX, maybe we could inject bounds checking in there as an option for us if we want to debug. Because when we generate PTX, we'll be removing all the bounds checks and everything, but we could actually enhance it and have options. So this code reflection is quite powerful here, not only on the compute, not only to generate PDX, but to generate debugging information in kernels if we want to do so as well. So it gives us a lot of flexibility. So I think we're still experimenting with this kind of thing. And I think we've got a lot more to do here to experiment with it. Okay, I'm gonna look what the time is here. Okay, I'm going to go through some demos, so I hope the demo gods are going to behave today. So I'm going to show the Game of Life demo, and I'm going to go to examples here. I bet you can't see that. So here is that okay? Is that readable for everybody? The back. So this is actual hack code here. And this is the kernel, the compute method for life we showed already. And just show you there's nothing, I'm not trying to trick you here. This is the kernel for life, like so. And first of all, we can run this in Java, multi-threaded, using thread pool. So what this program is going to do is Gary found a program that does a digital clock in life. And so he slurped in the form of this program and put it into the grid. And this is the initialization of this program. So I'm going to run it in Java first, and we'll see how slow it is. So it may be 3 generations a second. You can see it sort of doing some computation on there. These You see there's an AM and PM. I shouldn't scroll there, I might lose it. You can see the digits slowly appearing here, but you can see it's about, so that's a Java, I don't know how many cores this CPU has, multi-threaded exit disk. So let's run it on OpenCL instead. So we're going to generate, what's this going to do? It's going to compile that kernel to OpenCL C99 code. And it's going to, I believe it's also going to optimize the data movement as well. I will show you the output in a moment once it's running. So when we start this, so that's 10x. So it's about 3 generations a second. It's now 32 generations a second. And you can see, if I keep talking, you'll see the digits appear in the game of life running. So it's a pretty heavy, embarrassingly parallel computation, but you can see the speed up already. We didn't have to change any Java code here. We just wrote constrained Java code, but reasonable Java code, but we could compile to a GPU. And I think there's more optimization on the table here that we can do. But if I run this on my laptop, it's nowhere near as good. Hence, I'm using Ruby's laptop. Ruby is an intern that's been working with this, is helping on HAT, and she's been working on generating PTX code. So you can see the digits. I think it's starting at 12 there, coming into play. So I might be able to briefly show this. There's a lot. Actually, let me quickly run it again. I wanted to show the output. So it might be hard to see. I don't know if I can zoom in on this one. No, I can't zoom in. There's the detail here for the GPU. See a max group work size of 256. Then we see the code model for the compute coming in here. Then we see the code model for the compute transformed. I'm trying to find then we see the code model for the kernel. And we see what I talked about earlier with high-level models. We can see the structure of the conditionals, of the control flow, the if loop here. So you'll see nested structure coming into play here. That nested structure is important because it makes it easier for us to translate to C code that has similar nested structure. Eventually, we'll see the OpenCL C code coming in. So here we go. Here's the C code. Here's the structures we generated from the schemas. And here is the OpenCL C99 code generated from a model like so. So there's still work to do in this code generation, but we're getting pretty sophisticated in what we can generate. Okay, another demo. This one is a healing brush demo. I do not have an LLM demo, if you're thinking of asking. But actually, a segue into this. I think the right approach for improving HAT is we implement as many examples as we possibly can from a broad set of use cases. One of them is LLM stuff that I think we could implement. There's a potential lot of lift and shift over from CUDA and OpenCL to HAT. And every time we do a new example, we'll run into problems. And those problems are informative to see where we're falling behind or when we can't do something, or it may shift in how we design something. So if you want to contribute, one area to contribute is examples. So I'm going to go to the healing brush demo now while I speak. So the healing brush demo is you sort of locate a blemish and you locate it and you say, get rid of me. There we go. We're good now. Looks good. So let me run it rather than explaining it. Up here. And I run it in Java first so we can get an idea of the speed. And then I show code. Oops. Wrong one, excuse me. Okay, so we have an image here. Unfortunately, there's a bunch of people in the image I want to get rid of. They're spoiling my photograph. So the idea is you can do something like this. You'll go away and do some number crunching, and then it disappears, like so. And so when I circled it and let go, it had to do a search in the image to find a similar part of the image as the boundary. And it picked one and then replaced it. And it took about 1 second on a small thing. This may go a bit faster the second time. It's taking about 1 second. So it removed this. If we do a bigger, it may take a little bit more. But so that did something weird. Look at that one. I did not ask for that. Yes, it's odd, isn't it? So that took longer because there's a bigger search space around. But you see how the search is the biggest thing. It's a brute force search through the image. I believe this was implemented on Android in RenderScript. So let's look at the OpenCL version. I will show the code in a bit, briefly. So we can, hopefully that will work, like so. So the first time it might take longer because it's generating the kernels for the first time. Afterwards, it's cached them. Let's try this again, see if we get any better luck. This is not related to GPU or CPU, but you see that's a lot faster. That's 50 milliseconds instead. So and that was on a bigger image. I don't know what would happen here. So, but it's pretty blindingly fast compared to running on the CPU. And you argue this is more real-world code than game of life. So we see a lot more. I can't zoom in here. There we go. We see a lot more reflected code and utility methods. So if this is the best fit that tries to find another area in the image, and that's the compute here. So it's getting more real. This example is getting more real world. And even though we're using interfaces for the data, it's not, I don't think, at least in this case, it's unduly compromising the ability to code to it. It's not as nice as coding, say, with list hash maps or natural arrays, but maybe we can get there later on in some respects if we can abstract arrays out and leverage operator overloading. Maybe there's other ways to do this. But point is, it's real world stuff that's actually happening here. It's very visual stuff. It's not machine learning stuff, but pick your favorite machine learning example and it should be applicable, but they don't make great demos in the same way. We're also starting to implement Black-Scholes as well. Ruby did this. So it's just a very simple arithmetic calculation, parallel. The challenge for Black-Scholes is on something like PTX, is PTX does not have log instructions. You have to generate the functions that do the log. And the CUDA compiler does that for you. And we found out in PTX, we have to generate our own log and EXP functions. So it's interesting. I don't know what it's like on SPIRV. Is that the same thing for SPIRV? Okay. Bit better, yeah. I want to just show the Mandelbrot demo. I don't think any GPU, so this is on the CPU. And this is on the GPU, OpenCL. So, yep, same code. All right, back to slides. Okay, I showed the healing burst demo. Okay, so hopefully you've got a reasonable idea of how we're defining the HAT programming model. We've still got a lot of work to do to make it crisp, but we got something that's workable and something we can learn from through iterative example. And I think it's really showing the benefit, first of all, the benefit of Panama. It really is, and I think it's helping to show the benefit of code reflection. An important aspect of HAT is providing feedback to Babylon to make it fit for purpose. So we're learning on how it's using what is missing from the APIs, so we can get that feedback loop going as well. Not only to prove we can build a very solid and powerful library in Java that does GPUs, but at the same time to improve the technology that we are using to enable that to happen. So what next is just cranking out more of this stuff. I think collaboration is one of the most important things we can try and encourage, both from the vendors and also people interested in using this and writing examples for it. Because I think examples will be one of the best ways we can get feedback on it. So there's a lot of work to do on the implementation and design, but it's moving in the right direction. So if you want to help us, please help us move it in the right direction. All right, thank you.